Okay, so now we are trying to design a VCO in 45 nanometer CMOS technology. The specifications for the VCO we have already derived. So for this specification, we are going to make some design choices. So we are going to assume that the maximum inductance which we can have is 3 nanohenry and the corresponding quality factor is going to be 10. So this gives a maximum RP of around 924 ohms. And we find that even for this value of Q and the RP, the phase noise is much better than what is needed to meet the specification. So we will go with this maximum RP and the maximum inductance value, which also gives a tail current value of 1.7 milliamps. So let's see how to do the design in this technology based on these design choices and the given specification. So let us instantiate a MOSFET with the medium channel length, which is 45 nanometer in this process. And let's increase the finger width and make the number of fingers also a variable. And we can add a current source. Right now we are keeping it 1.7 milliamps. This value is needed to meet the output amplitude specification for the given RP of the tank. Now we can also add the inductor. Since we also want a center tap point, so we will instantiate two inductors. Of 1.5 nanohenry each. We also need a capacitor. So for now, we will model all the capacitor at the output of the VCO as a single parallel capacitor to the tank. Let's call it CP. And we also need a parallel resistance to model the tank loss. Let's call it RP. So here we are just trying to figure out what should be the cross-coupled MOSFET sizing so that for this kind of tank, it will be able to result in oscillation which meets the amplitude as well as the phase noise specification. We also need to add DC supply. So the supply in this process is 1.1 volt. Now we can make this cross-coupled connection. And let's label the output nodes. So this is a schematic of a very basic cross-coupled LC oscillator, where we are using this ideal inductor capacitor and modeling all the losses RP. There is no varactor, there is no cap bank, and also the loading at the output due to the buffer is all taken into account by just a single CP capacitor. So first thing what we need to decide is the headroom for this tail current source. So let us start with a headroom of 200 millivolts. So to enforce this headroom of 200 millivolts, what we can do is we can just put a voltage source in parallel, which is equal to 200 millivolts. So it will ensure that the source node of these MOSFETs are always at 0.2 volts. And then based on what is the actual bias current in the MOSFET, we can scale the sizing such that the net current in the MOSFET is equal to the I0. So now let us do a quick DC simulation to find out what are the DC currents flowing in this MOSFET. So first we will add some variables. So we will also add a variable Q. We are assuming Q to be equal to 10. The center frequency for this design, VCO, we will take as 4.9 gigahertz. So now we can see that this CP value is going to be 1 by omega VCO square into the parallel inductance. So here it is 6.28 into FVCO square into the inductance value, which is 3 nano. Number of fingers for now, let's just keep as 1, and based on how much current is flowing in the MOSFET, we will scale this value later. The RP value, we can again calculate from this Q and the inductance value at 4.9 gigahertz. RP value will be equal to Q into omega VCO into 3 nano. Now, based on these variable values, we are going to do a DC operating point simulation. Okay. So now let us check what is the bias current we are getting in the MOSFET. So here we can see that these MOSFETs are having a bias current of 0.17 milliamps each, whereas what we want is total current of 1.7 milliamps. So, and at the same time, we are also getting a GM of 0.57 millisiemens. We need to make sure the GM is high enough such that we have a startup gain which is much more than 1. So we will target a startup gain of at least 2. First thing we can do is we can try to scale the current in this MOSFET so that the total current is equal to 1.7 milliamps. Okay, so now we can see that this current is going to be around 1.5 milliamps. So it's 0.75, 0.75 in each of these MOSFET. Based on these currents, we will find the startup gain. And if, let's say, the startup gain is not sufficient, then we have to find ways to increase the GM. So here we can see that the startup gain is coming out to be close to 1.1. So normally we want a startup gain of at least 2. So in this case, if you want to increase the startup gain for the same RP, we have to increase the value of GM. And if the current is also fixed, then one way to increase the GM is by reducing the VD set. Since we can see that in this circuit, VDD is directly deciding the gate voltage and the gate overdrive. Let's say we are not touching the headroom which is given for the tail current. Then in such a scenario, by reducing the VDD, we can reduce the gate overdrive. And for the same current, we will be able to improve the G. So let us reduce the supply 0.9 volts. And now for this value of VD set, we want to again increase the current such that the total current is equal to 1.7 milliamps. So here we can see the current is only 271 microamps. So if we increase the number of fingers till 12, now we can see that the current is close to 0.9 milliamps, not exactly 0.85. So at the same time, we can also see that now the GM has increased to 5.9 millisiemens. So now we can remove this voltage source, and since the total current in this two MOSFETs is close to 1.7 milliamps, we'll find that this tail node will also be maintained close to 0.2 volts without this voltage source. So now we can see without a voltage source for 1.7 milliamps tail current, we are getting a tail node voltage of 206 millivolts, and the GM of both the MOSFETs are now 5.8 millisiemens. So for 5.8 millisiemens, we are getting a startup gain of 2.7. So now we are ready to do a transient simulation to verify whether the oscillator is oscillating or not. So here we also need to set an initial condition to the output nodes in such a way that there is a small asymmetry when the transient simulation is started. This asymmetry is going to push the oscillator to start the oscillation. Otherwise, because of the symmetry, both the node voltage will stay at their nominal value, which is the VDD voltage, and we will not be able to see the oscillation. Now in real world, there is always some noise present in the circuit, which is going to push the oscillator to oscillate. But in transient simulation, there is no noise. So we have to externally add some asymmetry in the circuit. So here we are setting one of the node voltage to be 1 volt, so that there is a 100 millivolt difference between the two output voltages, which is sufficient to trigger the oscillation. So now we can see that the oscillator is oscillating, and here we can also see that the output amplitude is around, this is 1.38 till 0.418. So the differential amplitude is slightly less than 1 volt. We designed for 1 volt, but it's coming out to be slightly less because the swing is pushing the MOSFET close to the linear region. And now we can find what is the oscillation frequency, and this can be done with the help of harmonic balance simulation. So this analysis is available in RF simulators. So it allows to find the steady state behavior of a circuit in the presence of large signal. Here we can give an estimated frequency. So we are assuming it should be around 4.9 gigahertz. And since it's an oscillator, we will mention the output voltage nodes. Now we can find the output frequency. So here we are getting 4.868. We tuned it for 4.9, we are getting 4.868 because there is some parasitic capacitance of these MOSFETs. Now we can run a noise simulation on top of this harmonic balance simulation to find the phase noise. We will choose the differential output for phase noise calculation. Okay. So now we can plot the phase noise. So here we can see that phase noise has a roll-off of 20 dB per decade at high frequency offset. So at 1 megahertz it is getting minus 116 dBc per hertz. At 10 megahertz it is minus 136 dBc per hertz. So we wanted phase noise to be better than minus 98 dBc per hertz. We are already getting that. So our calculation told minus 118 dBc per hertz. We are getting slightly lower than that. The reason being the output amplitude is also reduced, and because of the output swing, the MOSFETs may also be slightly pushed towards the linear region of operation. But still it is sufficient to meet the required specification. This output frequency, call it VCO. Ref VCO is 4.8 gigahertz. Phase noise at 1 megahertz offset is minus 116.7 dBc per hertz. Here we can also add the output amplitude. So our differential output amplitude we can find from the output spectrum. So we can see that the output amplitude at the fundamental frequency is 970 millivolts. We can find this value at VCO, and we can convert this into the magnitude. This expression again we can add it to our outputs. B amplitude. This is the phase noise at 1 megahertz offset. Now we can see that we are getting a phase noise of -116 dBc per hertz. VCO frequency is 4.8 gigahertz and output voltage amplitude is 970 millivolts. And all these three are close to the specification which we wanted. Now to convert this oscillator into a VCO, we may need to add varactors and cap bank and choose the cap ratio such that we can cover the entire frequency range. So this circuit as such is not completely optimized. So more optimizations are possible in terms of the bias current and the sizing. But at least you have got the idea that how to design a functional oscillator and how to do the sizing for the transistors for a given tank.